In this 8th lesson, we'll take a look at active termination and what the oscilloscope patterns look like when we have problems with active termination. As you'll see, there's quite a bit of difference between what the pattern may do due to a failure when I have passive 120 ohm terminators or if I have a network that is actively terminated. This is the typical device that would be the active terminator. This particular one has 6 terminals. Most ag techs are very familiar with this device because these get replaced quite frequently, whether they're the problem or not. Oftentimes they seem to get replaced. So instead of having a passive 120 ohm terminator at each end, the CAN bus would have one of these active terminators at either end of the CAN bus. I know that John Deere techs refer to one of them as the active terminator and the passive terminator. As an electrical engineer, that's really tough for me to use that terminology, but I'll try to stick with it for this video, even though I may not agree with the terminology. In recent times, most manufacturers, I think, have went away from active termination and are using just passive termination, with the exception perhaps of the implements and the implement bus on some machines. So before I get into some of the details of the active termination, we kind of need to go through a little bit of refresher on some basic electrical. So you can see here that I have a circuit where I have 2 voltage sources. This is one voltage source. It is at 2.5 volts. Here's another at 1.5 volts. They share a common ground, and between them there is a resistor, this 100 ohm resistor in this case. Because one of the rules of parallel circuits is the voltage everywhere in a parallel circuit has to be identical. If I put my voltmeter here at this point, it's going to show 2.5 volts between, with the power and ground. On the other side of the resistor, if I put my voltmeter in place, it's going to show 1.5 volts. If instead of 1.5 volts, this were something, we'll say 4 volts, kind of looks like CAN voltages, we can see that this meter is showing 4 volts. It did not change the meter that is showing 2.5 volts. If I were to remove this resistor, if we just took it out of the circuit, nothing really changes. However, the thing that I can't do is remove this resistor and replace it with a short. I cannot I cannot have 2 different voltages in parallel with each other, 2 different values of voltage in parallel with each other, because the rules of parallel circuits say they have to be the same voltage. Therefore, they must become the same voltage, or we must burn the wires up that are connecting the 2 voltage sources, which is typically going to be the case. So if you try to take a 12-volt battery and put it in parallel with a 6-volt battery, you know just what I'm talking about. What's going to happen is if you were using jumper cables to do that, something has to melt, something has to give up. We're not allowed to do that. We're going to flow a lot of current and we're going to make a lot of heat. So as long as I've got this resistor in place, it's okay for me to have what appears to be 2 different voltage sources in parallel. And they're not really in parallel because we have this resistor in place. So this allows us to have different voltage values measured on either side. So here I have a circuit lab model, a basic elementary model of active termination. So I have 2 different controllers that I've modeled here, 2 different devices that would be connected by this CAN backbone. So here's CAN high, here's CAN low, and instead of the 120 ohm terminating resistors, I've put in instead these electronic devices. This is a very simplified model of what is contained within these typical terminating bias circuits, as they're called, or TBCs. So contained within them, typically I would have a very accurate 2.5 volt regulator, actually 2 of them. One would be on CAN high and one would be on CAN low. And I have some resistance, something like 100 ohms of resistance, if you would, between where this connects to the backbone and where this connects to the output of the voltage regulator. So looking at this is like my voltage regulator that is on, in this case, the CAN high circuit. We can see that it's able to hold this at 2.5 volts. So looking over here, this is held at 2.5 volts. That lets the voltage back here on the CAN bus go either to 2.5 volts or something up near 4 volts, which are the typical ranges for a dominant and recessive bit. So the same thing for CAN low. The low side, it goes to obviously the backbone. The other side is connected to in this case, terminal F of that device that I showed you previously. We can see at the other end of the CAN bus, we have an identical device. These are the same part number. These would be the same device, nothing typically different between them. Maybe different with ISO with implements, but typically on the machine, if it's on the machine network, these are going to be the same device. So these are interchangeable, typically the same part number. You can see that I have, in this case, I'm showing it being powered off a 12-volt battery. Of course, it would typically be off of ignition, or it would be controlled by some controller. Some other device would provide this power. We wouldn't leave this on battery because we don't want this to run down, but just to give you the idea here, I've got this shown going to 12-volt battery. So it comes through typically with that the device that I show here on terminal A. And so through terminal A, it goes to the device and it provides the power for these two 2.5 volt regulators. So these are both grounded and they ground back through pin C of that device. So whenever the power is on, this output of these both will be 2.5 volts. So I would have 2.5 volts present on this side of the resistor. Same thing that I had in the other circuit here. Here's my 2.5 volts, here's my resistor. So on the other side, or going to the other terminator, I'll use the terminology. So this is within some ag manufacturers, I'll say probably John Deere, this is referred to as the active terminator, even though both are technically active terminators. This is called the active terminator. This is called the passive terminator. As an electrical engineer, I do not like that term because this is definitely a powered device and it does not meet the technical definition of passive. So we can see that I have through terminal A, there is internally, and you can measure this with an ohm meter, you can see that I have continuity between A and B and between C and D. This is basically just a jumper that is contained within. I don't know if that it's physically a jumper, but there is a connection between pin A and pin B that does not require any logic or any electronics. It's just a physical connection. So whenever I plug this device in, I have terminal A, whatever I have on terminal A here goes to terminal B, so I'd have 12 volts here. That provides the 12 volts over here at terminal B. We do not use terminal A, there's no need to, right? And so this does the same thing. It powers this device. This is an active terminator, even though it's called the passive terminator. It is an active termination device terminating by a circuit at the other end of the CAN bus. Both do exactly the same thing from an electrical standpoint. Same thing for the ground when it uses pin C. The ground for this comes from pin D. So as most ag techs know, this power and ground are routed together, twisted in a quad pair throughout the entire machine. So CAN high, CAN low, and this power and ground are twisted together. This provides excellent immunity to something called electromagnetic interference, as do these devices. But you can see that these devices are doing the same thing as what the passive terminator does, but they do it better. So when the CAN network tries to, I'll go ahead and run the quick simulation of this. Hopefully this works. We'll do a time domain. We can see, so we went from our recessive state. This looks very clean, goes up very quickly to the dominant state and stays at those levels. So as I said, if you look at this on the scope, you might notice that it looks cleaner when you're looking at active termination versus passive termination. Maybe I should also mention, I have heard because this is now called the passive terminator, that this turns into a 120 ohm resistor. It does not. But so one of the other, I don't know what I would call it, stories that I've heard, the active terminator is responsible for providing the bias, the 2.5 volts for the CAN bus. This is true. It does, just like every other controller on the CAN bus. You can try this on your own. I've got one that I'll show on the oscilloscope. If you remove both of the active terminators, I won't say this for the ISO network, for the implement network, I've never tried it, but for sure for the machine network, if you remove both of the active terminators and put 120 ohm resistors Between E and F of those connectors, this CAN bus works just fine. It is held at 2.5 volts. Granted, yes, it does help maintain that 2.5 volts during the recessive state, but each controller is responsible for putting that 2.5 volt bias on as well. These devices just help regulate that better. As I said, they do a better job, but I guess it's been determined that we don't really need anything that does that good of a job because, as I said, these have been eliminated over the years and replaced with 120 ohm terminating resistors. What I'm going to do next, I'm going to show, as I indicated, there's some differences as to what you'll see with active termination versus passive. So one of these is if I have an open at one of the controllers. We know what it looks like with passive termination. CAN high follows CAN low, or CAN low follows CAN high, depending on which controller it is. So here I've opened this device, which is going to be putting a dominant bit on the CAN bus. We'll take a look at what that looks like. And we can see that instead of CAN high following CAN low, CAN high is locked or held at 2.5 volts or approximately 2.5 volts by that terminating bias circuit. So it puts a stronger 2.5 volts on the bus, if you would, than we have with passive termination. There is nowhere for, I don't have a low impedance path like that 120 ohm terminating resistor that I did with the passive termination. I don't have a path for that to pull down and to basically become the same voltage as CAN low. So we'll go ahead and we'll close this guy again, and we'll take a look at what you can imagine what it looks like when I have a problem on CAN low. So we're going to open CAN low, and when I open CAN low and we run the simulation, it does the same kind of thing. Instead, CAN low is held at 2.5 volts, and CAN high increases up to whatever it's going to be, the 3.5 volts or so. So we'll take a look at some actual oscilloscope traces, what that looks like when we introduce those same failures. But this is one of those differences. The same are going to be true for the shorts to ground. Those scope patterns look different. We'll take a look at those scope patterns then. Okay, so taking a look here, this is an actual failure that we found in the field on a John Deere S660 combine. This had complaints of very intermittent problems with DTCs and with engine speed changing and surging. So if we zoom in on this, we can see that at some point or another, we have this problem. So here's my 2.5 volts approximately. And as we take a look at each of these bits, we can see that we're able to drive CAN low down to the dominant bit state, but CAN high is virtually staying up here around the 2.5 volts. This machine does have active termination. So while that device that had the open circuit, if you would, at CAN high, it was an intermittent open of CAN high at the device. Here's another device that's on the network that's able to communicate just fine. You can see the problems, the real problems that this thing was causing, because that device it wouldn't shut up. It just kept communicating. It couldn't get a response from anybody, so it kept trying to get its messages out on the CAN bus. In the time being, the engine controller cannot get the messages from one of the vehicle controllers that is probably the EIC that is trying to tell it what engine speed to go to, so the engine ends up dropping down to a low idle speed. So this is a real instance where we have an open on CAN high. As we can see, it held at 2.5 volts. I have other instances or other examples where I have the mirrored image of CAN low. We'll take a look at one of those. Okay, here's another machine, and in this machine we had an issue with CAN low. We had a terminal that was not making good connection at a controller, at one controller. This is an actively terminated CAN bus. We can see there's our approximate 2.5 volts. In this case, CAN low is pretty much staying at 2.5 volts, while CAN high is able to go to that dominant bit state. We can see my other controllers were driving CAN low to the correct level for a dominant bit with no problem, but the controller that has the problem, that is the one with CAN low is open. We'll go through in other videos where we actually show how to decode this and to be able to determine which controller is causing this problem, especially when if this is an intermittent issue. Okay, so this is another machine which is actively terminated. So intentionally I shorted CAN low to ground. We can see out here when that happened. We got, I said I tried to make it like an intermittent short. So sometimes I was briefly making contact, as in this case. But we can see, if you recall from passive termination, if I short can low to ground, there's a good chance I might not even know that it happened because can high is still able to drive up to the dominant state. With active termination, this is not possible. Because of the electronics within that terminating bias circuit, we end up with, in this case, can high sitting at about 2.5 volts and can low, of course, down near very close to ground voltage. This is a negative voltage. It's 12 thousandths of a volt negative. It's virtually zero. So this is a failure where can high was intermittently shorted. You can see here that I'm bringing it back. I said if this were very fast, it would be you wouldn't be able to see it with a multimeter. But if you did have this failure in place with your multimeter, these are probably the can voltages that you're used to seeing on an active termination when I have a short to ground of can low. Okay, so this is that same machine, active termination. In this case, instead of shorting can low to ground, I shorted can high to ground. So we can see in this case our yellow, our trace, our voltage, we're down near about 0 volts. So this is only 5 thousandths of a volt. Of course, it's shorted to ground. If I look at can high, can low, we can see that can low, we can see some dominant bits or an attempts at putting dominant bits on the CAN bus. This definitely looks different than what we have with the passively terminated network, but we can definitely tell by this value of near 0 on can high that it is shorted to ground. Once again, with a multimeter, not hard if this is in place, but if this is something that is intermittent and very brief, may be tough to catch it with the multimeter. So in this case, what I did, this is on a real machine. I pulled the ground, or removed the ground terminal from the so-called alleged passive active terminator. So the terminator that only has 4 wires, I removed its ground. Therefore, it doesn't have any power. And you can see what this has done to the CAN bus. This is garbage. I can't do anything with this. So we have these voltages, if you would. So I have can high or can low sitting at a voltage near 6 volts and can low or can high near 2.6 volts. Why this occurs, I can't actually say because I don't have the full schematic for what is inside the terminating bias circuit. That device is apparently trying to find a ground someplace, and it finds it apparently trying to find it through one of the CAN terminals, through one of the harnesses. So whenever you take the ground away from the passive active terminator, this is the pattern that you're going to get. You can see that that active terminator by itself was not able to hold this network in place when I pulled the ground for that passive terminator. So in this case, I removed the active terminator, same machine, and I only had the passive terminator in place. So that so-called passive terminator would not have any power. So because the active was not connected, it didn't have any power. We can see that no communication is possible. The reason we have the voltages at this level, as I said once again, there are electronics within that terminating bias circuit, and they're apparently pulling it to this level. If I were to then go to that active terminator connector and I jumpered from terminal A to terminal B with a jumper wire and from terminal C to terminal D, this CAN bus would have recovered because I would now be powering that so-called passive terminator so that it would terminate the harness. Granted, it's not as good as having one at both ends, but that would function. Same would be the case if I removed the passive terminator. If I took it off of the harness, the so-called passive terminator, and only had the active terminator, the 6-wire in place, the CAN bus, as most of you know, will probably recover. I won't have any issues with it. We don't want to leave it that way, but it should be good enough to function. Okay, so same machine, and this time I removed both terminators. So I do not have the active terminator nor the so-called passive terminator connected to the harness. We can see that this looks very much or identical to what we see on the network, my bench network, where I didn't have the 120 ohm terminators in place. We can see the capacitance of this network. We can see that the wiring harness, the devices, we have this decay, this time for a decay. So it's trying to drive up to a dominant bit, and because it thinks that other devices are on the network that are more important to it, it stops communicating. And the reason for that is this decay. This time for this to occur is too long. We cannot pull the can high and can low back to the recessive state fast enough to be counted correctly time-wise as a bit. Okay, so in this final case, what I did is with both of the active and the so-called active passive terminator removed from the machine, I placed a single 120 ohm terminating resistor at the diagnostic connector. So this is somewhere towards the middle of the circuit. So this is a machine which originally came with active termination from the manufacturer. And I removed the active terminators completely so the electronics of those devices wouldn't affect the network. And I installed one single 120 ohm resistor. I didn't put one at either end, but you can see this network now seems to be pretty well restored. I don't have any error frames. All communication is restored. So the machine, even though it was designed with active termination, in this case, I put a 120 ohm terminating resistor across can high and can low, towards the middle of the bus someplace, definitely not where it's supposed to be. But just for testing purposes, I was able to determine I don't have a problem with this machine as long as my termination is functional. I've been asked before, can you do this as a test? I'm not going to tell you one way or another on that. I'm just going to show you that I did this and it didn't cause a problem. What I would not do is operate this machine on the highway or on the road or anything anywhere without with whatever the manufacturer has specified. So they specified this as active termination. You need to replace the devices with active termination. But just showing you that really there's not something magic about a machine that has active terminators. We're still able to each device hold the bus at this 2.5 volt bias. I don't know, there's 20 probably some controllers or devices on this CAN network, and each one of them, for what they measure for a voltage, are trying to hold that to 2.5 volts, the CAN transceiver in each one. Just like any other newer machine, this was an older machine, maybe I don't know, 10 years old or so. And so, yes, it came with active termination. A couple of years later, that same machine would have came with passive termination. Pretty much all those controllers are the same. The only difference is instead of 4-wire quad CAN wire, it's going to just have the 2-wire twisted pair like most truck techs are used to seeing. So now that we've gotten a lot of the theory out of the way, we can actually take some of that information in future videos and use that to diagnose and hopefully pinpoint exactly where our problem is with the network.